Hello. In the last lecture, we have discussed the details of Bell Coleman cycle. This Bell Coleman cycle is also called it as a reverse Carnot cycle, reversed Breton cycle, or Joule cycle. And then we have discussed the various processes of Bell Coleman cycle: isentropic compression, constant pressure, heat rejection, isentropic expansion, and constant pressure heat addition process. Now today we will discuss how the COP of Bell Coleman cycle is calculated. So consider the unit mass of air, means mass of air is as 1 kg. So the refrigeration effect is equal to the heat absorbed by air in cold chamber. Means what? The how much cooling effect will produce, that is equal to the heat absorbed by the air in the cold chamber. It is equal to the refrigeration effect. So therefore Q1 is the process 4 to 1 heat addition is equal to mCp into T1 minus T4. Heat absorbed or heat supplied to the air or heat absorbed by the air is equal to Q1 is equal to Cp into bracket T1 minus T4, because mass of air is considered as a 1 kg. Now during process 2 to 3, heat rejection process is there, and during that heat rejection process the amount of heat rejection is Q2 is equal to mCp into T2 minus T3. So m is 1, so therefore T2 minus T3. So therefore net work input is equal to, how we are calculating the net work input? Heat supplied minus heat rejected. Net work input is calculated as heat rejected minus heat absorbed or heat supplied. So Q2 minus Q1. So Cp is common in both cases. So Cp into bracket T2 minus T3 minus Cp into bracket T1 minus T4. Cp is taken out of the bracket, so that into the bracket T2 minus T3 minus T1 minus T4. Now net work input is there. We have to derive the formula for the COP of Bell Coleman cycle, and we know the formula for COP. It is the refrigeration effect to the work input. Now in this problem, the refrigeration effect is the heat absorbed or heat absorbed by the air, that is Q1, and work input is Q2 minus Q1. So COP is equal to refrigeration effect divided by work input, which is equal to Q1 upon Q2 minus Q1. Now Q1 is equal to Cp into bracket T1 minus T4 divided by work input is Cp into bracket T1 minus T4. Work input is Q2 minus Q1. Q2 is Cp into bracket T2 minus T3 minus Q1 is Cp into bracket T1 minus T4. Again, numerator is having Cp and the denominator is having the Cp. So Cp is taken as a common and cancelling with the numerator. Hence the COP is equal to T1 minus T4 divided by T2 minus T3 in another bracket T1 minus T4. Now this process is isentropic process. Process 1 to 2 and process 3 to 4. So consider this isentropic process, or which will be called it as a reversible adiabatic process. So for reversible adiabatic process, T2 upon T1, the relation between temperature and pressure is T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma, where gamma is adiabatic constant and its value is fixed 1.4. But this P2 upon P1 is called it as a pressure ratio. P2 upon P1 is called it as a pressure ratio, and it is denoted by Rp. Please remember T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma upon, so that P2 upon P1 is a pressure ratio and it is denoted by Rp. So the equation is T2 upon T1 raised to is equal to Rp raised to gamma minus 1 upon gamma. Now for 3 to 4, same formula, T3 upon T4 is equal to P3 upon P4, but P3 and P2 is same because constant pressures are there, and P1 and P4 are same. So therefore again P2 upon P1 raised to gamma minus 1 upon gamma, and similarly it is a pressure ratio, so T3 upon T4 is equal to Rp raised to gamma minus 1 upon gamma. If you observe these two formulas, equation number 2 and equation number 3, so right hand side is same, so we are equating with the left hand side. T2 upon T1 is equal to T3 upon T4. So by taking the cross multiplication, we are taking as the equation number 4, and after taking the cross multiplication, T4 upon T1, T3 upon T2, that again equation number 5. Now consider equation number 1. Consider equation number 1. What is this equation? COP. COP is equal to T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Now if we take T1 as a common from numerator, if we take T1 as a common in the numerator, now what will happen? In the bracket T1 minus T4, so T1 is taken as a common, so 1 minus T4 upon T1 divided by, from the denominator first bracket T2 is taken as a common, so inside the bracket 1 minus T3 upon T2 minus, again we are taking T1 as a common, so 1 minus T4 upon T1, but here T3 upon T2 is equal to T4 upon T1 from equation number 5. So hence we are calculating the terms in the numerator and denominator. Please look at here. In the numerator, inside the bracket, T4 upon T1 is there, and in the denominator, first bracket, T3 upon T2 is there. But if you observe the equation number 5, T4 upon T1 is equal to T3 upon T2. So if we put there and if we taken as a common, so numerator bracket and denominator bracket gets cancelled out, and only there is T1 upon T2 minus T1, or you can write it as T4 upon T3 minus T4. So first we will consider the COP is equal to T1 upon T2 minus T1. Now consider the equation number 2. So equation number 2 is T2 upon T1 is equal to Rp raised to gamma minus 1 upon gamma. Rp raised to gamma minus 1 upon gamma. So T2 is equal to T1 into bracket Rp raised to gamma minus 1 upon gamma. Put this value of T2 in here. So COP is equal to T1 upon T1 Rp raised to gamma minus 1 upon gamma minus T1. So T1 in the numerator and denominator is taken as a common and cancelling the terms. So T1 gets cancelled out. So only the COP of the Bell Coleman cycle is 1 upon Rp raised to gamma minus 1 upon gamma minus 1. So which is the final formula for the COP of a Bell Coleman cycle, which indicates that the COP of a Bell Coleman cycle is a function of only the pressure ratio. Only the pressure ratio. So please note this formula. COP of Bell Coleman cycle is equal to 1 upon Rp raised to gamma minus 1 upon gamma. In some cases we observe COP is equal to Rp raised to gamma minus 1 upon gamma minus 1 raised to minus 1. So both the problem cases are similar. But this is all about the isentropic process. If the processes are adiabatic process or polytropic process, so in case of polytropic process, the friction is considered, and for the polytropic processes means the process 1 to 2 and process 3 to 4, the PV raised to gamma is equal to constant. The gamma is not fixed. So at that time, when the polytropic processes are there, we have to consider PV raised to n is equal to constant. So therefore, the COP of the cycle we can determine as work done by the compressor and work done by the expander. So work done required for the compressor is, for a polytropic process during process 1 to 2, WC is the work required for the compressor is n upon n minus 1 into bracket P2 V2 minus P1 V1, and you can take it as PV is equal to MRT, so where M is the unity. So again R into T2 minus R into T1, R is taken as a common, so the work done by the compressor is equal to n upon n minus 1 into R into bracket T2 minus T1. Similarly for the expander, n upon n minus 1 into R into T3 minus T4. Now work delivered from the external source, that is a net work done. So W is equal to work done by the compressor minus work required for the compressor minus work done by the expander. So we are taking the subtraction. So n upon n minus 1 R is taken as a common, and inside the bracket T2 minus T1 minus T3 minus T4. So the heat absorbed during process 4 to 1 is Q4 is equal to Cp into bracket T1 minus T4. So therefore COP is equal to Cp into bracket T1 minus T4 divided by net work done, that is n upon n minus 1 R into bracket T2 minus T1 into bracket minus T3 minus T4. But we know that R is the Cp minus Cv, and sigma is equal to Cp upon Cv. So therefore R is equal to Cv into bracket sigma minus 1. So therefore COP is equal to Cp upon Cp into bracket T1 minus T4 divided by n upon n minus 1 into Cv into bracket gamma minus 1 into bracket T2 minus T1 minus T3 minus T4. Now Cp upon Cv is again gamma. So therefore COP is equal to T1 minus T4, only the remaining inside the numerator, and in the denominator that gamma is taken to the denominator's denominator. So n upon n minus 1 gamma minus 1 upon gamma into bracket T2 minus T3 minus T1 minus T4. So this is the formula when we are considering the polytropic processes.